In this presentation, we'll take a look at friction and see how it is entered into various calculations. So to begin with, we have the most fundamental relationship, which is between friction and the normal. So F is friction force and is normal force. And what we discover is that there's a direct relation between the two. As the normal force increases, the friction increases in direct proportion. The coefficient of friction is simply the slope of the line, or friction over normal. So let's consider a block on a surface. Over on the left here we have the weight and the subsequent normal force. Nothing else going on. In the middle situation we have the weight, the normal force, and we apply a force. When we apply a force F, then static friction resists that force. And if, in this situation at least, there's no motion, so if there's no motion, then the friction force is equal to the applied force, F. And that's got to be less than or equal to the maximum amount of static friction force we can get, which is mu s normal. Now, on the third one, we have the weight, the normal, the applied force, which is going to be a little more variable. So potentially we're going to take that applied force and exceed static friction so it starts sliding. Well, let's say we have a constant speed not equal to 0, so it's moving. So if it's moving at a constant speed, not accelerating, then the kinetic friction is equal to the applied force because they're in balance. There's no acceleration. So that's mu k normal, but that's true all the time. Anytime you consider kinetic friction, it's mu k normal. It's that value. Because sliding friction has a value. The coefficient of sliding friction is basically a constant, and it's only applied when it's moving. So there's no variability there. So it's also true that the kinetic friction can be less than the applied force if the acceleration is not equal to 0. So if it's accelerating, increase the applied force beyond the kinetic friction, then you'll simply have the kinetic force being the same thing it was moving at constant speed, and now it's less than the applied force. Okay, so that should all be pretty straightforward. So the static friction, as a definitive statement, is less than or equal to mu s normal. Equal when it's at its maximum value. The kinetic friction is mu k normal. So those are the two expressions. And of course, this less than or equal to simply denotes the fact that the static friction can be less than its maximum value. If it is at its maximum value, if you keep increasing F until you get to mu s normal, then we have a condition in which we describe the motion as impending. Motion impends. It is at that transition point between beginning to move and sitting there, motionless, held by the maximum static friction. Let's gain a little insight into the coefficient of sliding friction. We start with a block on a ramp. The weight is mg. And it's moving down the ramp in such a way that it's at a constant velocity. So you increase the angle of the ramp until the block starts sliding down, say. Moving at constant speed. So that's a special condition, right? Well, let's do a quick free body diagram. We have the x and y coordinate system chosen in such a way to be logical. So here's our block, weight acting straight down. The friction force, of course, since this thing is moving down, the friction force is the opposite way. So I have it drawn this way. With the gravitational influence acting down the ramp, W sine of theta. So that's going down the ramp, of course. Now, we also have W cosine of theta. We've just accounted for the entire weight vector, resolved it into its components, and then we have the normal. So with this, we can express the forces in the x and the y. So in the x, we have mu k normal, which is the friction force, minus W sine theta, the gravitational influence down the ramp, is 0. They're in balance because it's moving at a constant velocity. Forces in the y, we have normal minus weight cosine of theta, and that's 0. So those two expressions. Let's solve for mu k. Well, mu k we know is friction over normal. And now we recognize that the friction force, this force here, is just W sine of theta. So W sine of theta over normal. But the normal force equals W cosine of theta when we bring this over to the other side. So there we go. W sine of theta over W cosine of theta, tangent theta. So in general, we can state that the coefficient of kinetic friction is tangent of the angle at which a block will slide at a constant speed down the ramp. Isn't that awesome? Well, let's look at yet another way to find the coefficient of kinetic friction. Of course, we have kinetic friction is proportional to normal. It's equal to mu k normal, or mu k is friction over normal. Let's put a block of mass cap M, or big M, on a table, connected to a block of mass little m over a frictionless pulley. And little m is going to pull big M, and it's going to slide along this table at a constant speed. Let's do free bodies for both blocks. Big M, we have mg, we have normal, we have tension, and of course, since it's moving to the right, we have friction to the left, kinetic friction. Little m, we have mg, and we have tension. Velocity is constant, so A is 0, and the sum of F is equal to 0. So we can say that the tension equals the kinetic friction, but that's the same tension here, so that's also equal to little mg. Over the normal force is equal to big mg. So putting this together, mu k is friction over normal, friction is little mg, normal is big mg. G's divide out, and we have that the coefficient of kinetic friction is the ratio of the masses in this unique and special configuration. All right, let's look at some examples. First example will be real easy, just to highlight the difference between kinetic and static friction. You got the 500 Newton crate pulled with a force of 230 newtons just to get it moving. But then 200 newtons will keep it moving. So that's related to the kinetic friction, where the 230 is related to the static friction. What are the coefficients of friction? Very simply, mu s, Fs over n, 230 over 500, 0.46. Mu k, kinetic friction over normal, which is the 200 over 500, which is 0.4. We always note that the kinetic friction is less than or equal to the static friction. In the second example, we'll use the same 500 Newton block. This time it's pulled with a force at a 30-degree angle. We'll call that force T. So this will be a little more interesting. How hard do you have to pull it to keep it moving at constant V with the given coefficient of friction? That coefficient of friction will be 0.4. And what's the normal force? Well, those things interact with each other, so it's not just exceptionally simple. So let's consider a free body diagram with the y and x coordinates as indicated. So here's our block, mg, normal, and tension. The real force is acting on it. In addition to that, a real force, kinetic friction, which is coefficient of friction times the normal, so 0.4 normal. All right, so let's break tension into its components, T cosine of theta, T sine of theta. Wiggle out T. Velocity is constant, acceleration is 0, so sum of F is 0. And that's nice. Sum of F in the x, T cosine minus mu k normal, which is 0, and sum of F in the y. In this case, we have the normal force. In addition to that, we have T sine of theta. Bring that in. And in the opposite direction, we have mg. So minus mg equals 0. I don't have that. Well, from the first expression, we get that solving for t, we get mu k normal over cosine of theta. The second equation gives us an expression for the normal, which is mg minus t sine of theta. So here we have our drawing so far and our two equations that we're going to relate together. Expression for the tension and for the normal. Well, therefore, the tension is mu k normal, which is mg minus t sine of theta over cosine of theta. Well, we can multiply both sides by cosine of theta. We'll do that. So we have t cosine of theta. Of course, this mu k t sine of theta with a negative is brought to the other side to be plus t mu k sine of theta equals mu k mg. Let's factor out the t. So we just did that. And now let's solve for t. T is mu k mg over cosine of theta plus mu k sine of theta. Let's plug in what we know. Mu k is 0.4, mg is 500, cosine of 30 plus 0.4 sine of 30. Plug it in, and we get 188 newtons. Now, normal is mg minus t sine of theta, so the normal force is, of course, less than the 500 because it's diminished by the vertical component of the applied force, giving us a reduction in the 500 by 188 sine of 30, leading to 406 newtons. So there's the answer. And now, let's take this one step further. So now, let's determine the angle for the minimum tension, which will enable this block to be moved across the floor. Now, just as in the situation with the maximum range of a projectile, where you have opposing processes, you want to maximize your horizontal velocity, but also maximize the time. And those are antithetical requirements. Likewise here, you might say, well, we'd want to direct the T force all horizontal. So none of it's wasted in the vertical. You're all pulling horizontally, and that's going to be the minimum amount to get it to move. But of course, then the normal force is not diminished, so the friction force is maximum in that case. On the other hand, if you go too vertical to reduce the normal force, then there's not very much left of T in the horizontal direction. A vertical T does not do anything to get it to move horizontally. So you can see the problem here. Well, no problem. Let's just solve it. So we want to minimize T in this expression. This is the expression for T that we just solved for. To minimize that, what we need to do, of course, is maximize the denominator. So let's maximize this. All right. So how are we going to maximize that? It's two expressions here, two pieces of this equation that have theta in it. So theta is the key thing. So we're going to solve for y. We want to make this as big as possible. Y is as big as possible. It's cosine of theta plus mu k sine of theta. Well, let's take the way in which y changes with respect to theta, dy d theta, the derivative of y with respect to theta. All right, so minus sine theta plus mu k cosine of theta. There we go. Now, of course, we set that equal to 0. That'll be an inflection point, and that should reveal to us the angle at which this derivative equates to 0. So mu k cosine of theta is equal to sine of theta. We're left with at this point. So mu k is equal to sine of theta over cosine of theta. That's where it happens. Well, that's nice because that's tangent of theta. So theta equals the inverse tangent of mu k. Isn't that a beautiful little expression? We could stop now, but let's go ahead and stick it in because you probably were thinking it was 45 degrees, but instead its inverse tangent of 0.4. It's, of course, dependent on the coefficient of friction, in this case 21.8 degrees. Finally, let's take a look at what's called rolling friction or tractive resistance. Definition, similar to static and kinetic friction. In this case, the coefficient of rolling friction is friction over normal. Rolling friction over normal. Now, these values are small, ranging from 1,000th to about 3/100ths for a coefficient. Those are much smaller than we're used to in normal applications of static and kinetic friction. All right, well, fluid friction. We have basically two considerations and combinations of the two as well. It can get real complicated with fluid. Low speeds, generally the friction is proportional to the speed, and at high speeds, where you have turbulence, it's often proportional to v squared. One way to kind of get a handle on this is consider that work has the dimensions of force times distance. Think of this distance being a given amount. And that's equal to delta K, change in kinetic energy, which is change in 1/2 mv squared. So we see that the force is related to the velocity squared. The force we're talking about, though, is friction. So friction is proportional to velocity. Well, we'll deal with the concerns of work and kinetic energy at a later point. Let's do a rolling friction example. We have two bicycle tires initially moving at 5.2 meters per second. Now we're going to let them roll on their own, just give them a shove and let them start slowing down. Eventually they get to half their initial speed. Two situations: 40 psi tire, it's not very much pressure for a bicycle tire, takes 45.6 meters to reduce to half its speed. Pump it up to 105 psi, 213 meters. Let's get the rolling coefficient of friction for each one. So here's our tire, 40 psi, 5.2 meters per second, and it's going to reach half its speed in 45 meters. Free body for this situation. We have the weight acting straight down. Of course, we're considering this point of contact right here, right there. Weight, we got the normal, and friction. Which way is friction going? Well, it should be the opposite of the motion. There it is. Not very big either. All right, so sum of Fx is equal to ma, and that's also the rolling friction. So coefficient of rolling friction, friction over normal, which is mg. Let's go ahead and express the acceleration from a kinematics formula using the initial and final velocities. So there it is, v squared minus v squared over 2d. Now the final velocity is half the original, v0 over 2. So we're going to square that. And this gives us this expression, which reduces to minus 3 v0 squared over 8d. So mu r is friction over mg. Friction is ma. That is the sum of the forces. So we have a over g. Solve for a, so let's divide that by g, and there's our expression for the coefficient of rolling friction. And all that is variable here in this particular problem is the d, so let's go ahead and plug in the values, and we get mu r is 0.023, mu r2 is equal to 0.005. There you go.